Yeah, I got the normal distribution stuff up from before. Did you have a chance to get anywhere past? I think we did just before question 6.
Nope.
Yeah, sweet. All right,
9 to 5's
let's.
a hard.
9 to 5. Brilliant. Yeah, question 6. Hardness of metals.
This is tech able.
Oh, yeah, yeah, tech cable.
So how did VC results go?
Yeah, I mean, overall, decently. Yeah. Um, it was. Most people got what they were looking for, which is nice.
That's
And,
good.
yeah, it was interesting to see who did better than others, not necessarily based on um like how good they were at it, but like how much they'd improved over time. Because a lot of
Okay.
the people that come to us are usually struggling with methods and like want to get a 30 at minimum. And so even though the study scores that we were hearing weren't necessarily like super uh, big, like 40s and above across the board, it was good to see people going from basically no real skill at all to cool, we're comfortably above 30 and we're happy that we're there.
That's good. Okay. 0.90.
Uh, 0.90, let's have a look. 6A, point 0.9, yeah, that's good. Sweet. That's somewhat interesting. I can imagine a bit of a pitfall there.
Oh, okay. Okay. Let's see. 5.88, 5.87.
Yeah, that's good. Nice. I'm glad you went to calculate that rather than just do, oh, cool, it's roughly 2 standard deviations for 95%. So you can see approximately it's 6, but yeah, you would have had to have calculated that to be properly accurate. Granted, they didn't specify any accuracy here, so saying 6 might have still worked anyway. But yeah, well done. Either they're calling them specimens when they're metal.
9.
Yep, yep, roughly 9. That's good.
0.26.
Yep, 0.26 is good. Nice. Flying through these. This will be a fun one.
Mean and variance of P.
Mm. We've done something like this for a long time.
I mean, do we have like a number of trials?
Do we have a number of trials?
I don't think we do, right?
No. So we don't have a number of trials to work with. So the assumption would be you're doing it based on like the average per trial.
Okay, let's see. Okay, mean, I think it's 17.61,
You'd be
but
correct in saying that. Yeah, well
okay,
done.
cool. Variance. Variance is mean times 1 minus the probability.
That would be for binomial.
That wouldn't work here, yeah.
Yeah, we're not quite binomial here.
Variance is spread of results.
Yep,
So, what, -5 to 20?
not quite like that. That would be just the full. Well, even then, that would still be a bit weird because you'd be including everything between them when in reality you can only have one or the other. Variance is kind of like it's kind of like standard deviation, right? It's literally just the square of the standard deviation. Standard deviation doesn't tell you what the upper and lower is, but it tells you the rough separation of the distribution. That's the equivalent for variance here. There is an equation for it. How did you calculate the mean?
Mean was, okay, so I found the probability of having an acceptable specimen,
Yep,
multiplied that by 20,
yep,
and subtracted, when I did I multiplied the probability of an unacceptable specimen,
yep.
multiplied it by 5,
Hmm.
and then subtracted that number from the first.
Okay, that's good then. Um, yeah, what do I say without giving too much of a hint? Um, you thought binomial initially.
Actually, ooh, hold on. I'm trying to remember that when we used to do the probability tables.
Yes, that's what I was going to try and figure out some phrasing for without giving it away directly. Yeah,
It was
probability tables.
E of bracket x squared
Hmm.
minus E of x all squared.
Correct.
Okay,
Yeah, that's the one you're looking for.
cool.
So that works for literally all variance, and standard deviation is obviously just going to be the square root of that if you need it. Whether it's continuous or otherwise, you can use that equation. It's just going to be varying degrees of difficulty of doing that.
Yeah. Okay.
So typically you would use it for discrete, but technically speaking, it applies to literally all of the probability types.
Okay. We'll see. Oh no, this is not good. What have I done here? E of x squared minus e of x all squared. When you e of like bracket x squared,
Mhm.
is the probability that you square or
No, it's the x value. So
the x value?
whatever transformation stuff is on the x is applied to the x. Yeah.
Yeah, that makes sense. My variance is 54.03.
Yep, that would be good. Nice. Yeah, if you already had the working out for e of x, then literally what you had to do was copy those two lines and then square the x just beforehand. And then you're just subtracting the result of e of x and then squaring it.
Yeah.
So that's what it looks like if you're doing it in the most efficient way. You would go for your e of x, then you'd create your e of x squared, and then put a subtraction afterwards, just squaring the result of the first time.
Yeah. I've just been having like a bit of a problem like lately, right? So my calculator is like in exact mode.
Yeah.
So it gives me some like humongous fraction, which is okay, right?
Hmm.
And after that, I could control enter.
Yep.
But sometimes what
Oh,
happens is, right, when I could
yeah.
control enter, it like
It
it applies the
repeats it.
last like calculation
Yeah.
again.
Yeah. Whenever you have like ANS answer in your working, then it'll redo. Uh, it'll use whatever was previously calculated as the base of the next thing.
Yeah.
Um, yeah. What would have happened here? Because you would have done e of x, that would have been more or less fine. Yeah, I do wonder why. When did the ANS show up? When would that have shown up? Because you would have done e of x, which is just a one-liner, e of x squared, copy it down. Because when you copy it down, it doesn't actually show like ANS. You might have just done it a different way. But yeah, basically, if you're worried about that sort of thing and that's slowing you down and you're typing it out more, the key to look for is that ANS symbol. If that's there, then you're probably going to run into an issue. Otherwise, you'll be fine to control enter it. Or even better, just grab a copy of that fraction and control enter on that instead. Because grabbing a copy of something is really easy. Just highlight and enter.
Yeah, that's
But okay, cool. Actually, almost at the end of it, so we might as well do all these. We'll see if we'll see if this 8C ends up getting done. But I guess they are kind of giving these to you ahead of time. But anyway, we'll see if we get there. Question 7: weekly error. The whole concept of tracking time is so cool. Like how how you account for these sorts of drifts. A crazy setup. Oh, oh no. Welcome back.
Sorry about that.
No worries. Question 7: weekly error. So every week your watch is allowed to drift 5 seconds.
Find the mean and standard deviation of the distribution of error if 3% of watches are rejected for losing time and 3 are rejected for gaining time. Okay.
This is a decent question, actually. I like this one.
Yeah, that's what I'm thinking about. Okay.
We have done it before, but the way it's worded is quite cool.
Okay. Um, mean, I want to say 0,
Yes. Nice. Very good.
but standard deviation is all that's left to find.
Uh huh.
You know why I didn't say it with like more like conviction, Miles's? It's because bloody methods is such a like deceiving subject with
Yeah.
with the way the questions are written.
Yeah, for sure. And I mean, like, the good news is you didn't necessarily have to say mean is 0. There's enough information in here to do a simultaneous. But yeah, either way was a good spot. How's that going so far?
Not good.
Not
Mm.
good.
Z equations, right?
Z equations? Yep, that's
Except
good
I'm
then.
forgetting if I'm meant to put anything in Z or not.
Well, the
Because I
full,
know the mean.
yeah, you know what I mean, correct? What are we trying to find?
Trying to find standard deviation.
Yep. How do we normally find basically any variable in an equation?
You solve for it.
Yep. And solving for it is a matter of rearranging to get that variable on its own. Depending on the question, there might be letters that are still in there, but we're looking for a number here, so the other side of that equation has to be purely numbers.
Yeah. I need your help on this one.
Sure. Okay. So what have you gathered so far?
Mean is 0.
Mean is 0? Okay.
And yeah, that's about it.
About it? Sure. You mentioned something about an equation. What equation were you thinking of?
The Z equations.
Well, that's good. Yeah. So you got a little bit more than just mean is 0. Z is equal to x minus mean over standard deviation.
Yeah.
Z is equal to x minus 0. So basically just disappear. Standard deviation, and why not? Just standard deviation equals x over z.
Yeah.
So if we have an x and we have a z, we're happy. We win. What can we do to get those? Let's
Look
say
at
an x, right?
look at the information given to us. So
Yep,
for one of them, the X could be 5.
sure. X5, awesome. Maybe to make super clear what we're actually talking about, it'd be good to have a little picture of it. We know we got a mean of 0. Um, what's going to go on either side? So you mentioned 5 is one of the possibilities. Would that be on the right or the left?
Right.
Yeah,
Then -5 on the other side.
that's it. Good. And the reason why I'm doing this bit is um, to set up the probabilities that are in there. So if we're choosing to use the x equals 5, that's fine. So x equals 5, it just means we want to convert this one to a z. So what else can we start filling out on this picture based on the information provided?
On either side, so on the right side of 5, it's 0.03, and then
Yep.
on the left side of -5, it's also 0.03, so in the middle, 0.94.
Yeah, that should be good. Let me just double check that. Rejected for losing time, so means less than, yeah, both of those should be 0.03 either side. Yeah, so 3%, 3%, 9, 6. Cool. How do we normally get Zs?
Um, well, you usually get 3 variables and then you plug them into the
Oh, sure.
equation,
Okay.
but this time we
When you
don't
were
have that.
doing, remember the simultaneouses we were doing earlier with getting mean and standard deviation? We weren't able to get Zs via solving it like that. Do you remember what we did when it was a simultaneous?
No, I don't remember.
Okay. There's probability information that we haven't used yet. We've got this Z equation stuff that we've been working on. That's good. We've basically plugged in all the stuff we can so far into that. This is CAS enabled. When you have probability information and you're trying to find anything in the Z equation, there's one CAS thing that works out for that all the time.
Inverse normal.
Inverse normal. Cool. How do we use that?
You put an area in and
Mhm.
do its thing.
So if we care about this x value, what are we going to actually plug in?
0.97.
0.97. Oh, I calculated this. This is wrong. That's 94. Yeah, you're right. So 0.97 because everything left. And then, yeah, that'll get you the Z. Mean of... So that's actually interesting now because mean is 0 for both of these, but standard deviation should be different. Yeah, because plus minus 5, that will be... Yeah, that'd be a lot for the standard normal. But yeah, you're going to get some Z out of that. And, well, whatever you've got is just going to go under here.
Okay. So is the standard deviation somewhere around 2.65, 2.7?
Yep, that's good. That's the one. So, yeah, it looks like this sort of interplay between when you've got these Z equations and inverse normal. So how can we know to recognize these better? You'll notice there's X information given. You'll notice there's probability information given, and you're told to find a statistic. So I think the main thing here is that you're told to find a statistic. That pretty much next to guarantees you're going to be using inverse normal for something. We have
Yeah.
seen circumstances that we don't need it, but like a lot of the time, especially if you have to solve two statistics, you're basically guaranteed to need inverse normal there. Now, obviously, you haven't had time to practice this much outside of class, but now that you do have the time, these are the questions you're going to need to like smash out because all this other stuff, I mean, maybe not this, I have no idea what this is yet, but like all the other stuff that we've been doing, oh, I mean, I'll let you speak for yourself, but it seems like you got the gist of them.
Yeah.
It's mainly just this sort of stuff. So let's
Yeah.
see, maybe we'll just clarify like what questions those are. So it's question 7, obviously. Probably this question 5 that we ended up with last time. Anything that just says find mean and standard deviation, that'll be probably an easy thing enough to control F for. If I could type. And standard deviation. Oh, really? It's only... No way it's only in this chapter. That's crazy. Do they not have anything in the actual... Oh, that's right. No, they don't. Yeah, that's why it's doubly weird. Because when you go into... I think it's 16D, they start showing you how to inverse normal. Okay, now my control F is just broken. It just didn't find it. Cool. So 16D has them. I guess as soon as you see example 8, so here and down, there's going to be a fair few examples of those. And then just the tech active, so that multi-choice and extended response are going to have copies of those as well. Cool.
Yes.
Awesome. Oh, right, we didn't actually finish this one. Part B, probability that fewer than 2 are rejected in a batch of 10.
Below sequence time.
Yeah.
Okay. Yeah.
How's that going?
Almost there.
Okay.
I think.
Suppose we'll find out soon enough.
Probably that fewer than 2 watches are rejected in a batch of 10 such watches. Okay. So we want 9 successes at least.
Oh, okay. Yep.
We want 9 or 10 successes, and what were the successes this much? 0.88.
Yeah, 0.88 is good. How'd you go about doing that?
Um, so use the standard deviation from the last question.
Yeah,
Normal CDF, -5 to 5, mean of 0, standard deviation to find the probability of success,
yep.
and then Bernoulli sequence using
Cool.
that.
Bernoulli sequence or CDF.
Binomial CDF.
Okay, cool. Just wanted to make sure I use the CDF on that one. Yep, awesome. Yeah, they did it slightly differently. They did probability of failure, and then just worked off of that. It's the same thing though. There's no real difference. It's just a matter of what your p-value is going to become.
Yeah.
Nice.
No, lower and upper bounds as well.
Well, yeah. I mean, it's going to change your lower and upper as well. Yeah, you're right. So fewer than 2, so 0 to 1. Yeah. I'm curious to see where this is headed.
Eight. Okay, random detergent sold in bottles of 2 sizes. Yeah. Okay. Question 8A.
Mm-hmm.
I know this is gonna be a tree diagram thingy at the end, but
So you don't actually need a tree
oh,
diagram.
standard bottle.
Yeah. I see. I almost did exactly what you did, which is like, oh, I know this got a question. You got a 50-50 at the start, and then probability of each. Yeah, they actually made it a bit easier than that. But yeah, I almost did the same thing.
Okay, well that's not hard then.
No, not at all. That's chill.
That's just a normal CDF.
Mhm.
You see, like I don't believe the methods can be so nice to me.
Yeah. It's like, it's got to be harder. It's 8A. It's the last question. It's got to be hardest.
0.106.
Yeah, that's good.
Yeah.
That's obviously quite chill.
Find the probability of a box of 10 randomly chosen standard bottles contains at least 3 bottles whose contents are each less than 0.75 liters. Okay. Point zero eight.
0.08. Yes, that's good. Question C is a wild one. I'd be shocked if you can get it, considering that I'm still not understanding it, having reading the answers. They don't really show. Sorry, like the answers do more or less explain what's going on. They're more or less showing you like what actually does it mean to apply these sorts of transformations inside the E of x and the variance equations. The application of it is to find the probability there is more detergent in 4 randomly chosen standard bottles than in 3 randomly chosen large bottles. So here's what they came up with. Actually, go here. So the first thing they've done is define a new letter as this, 4x minus 3y. I can only assume the 4 and the 3 are coming from this. All right.
Yeah.
So x is there and y is there. And from there, probability of that has to be greater than or equal to 0. Y. Detergent. Yeah, I don't really get that. And then what do they do with that, assuming that that is the next step? You then expand it out with the equations that they've given, giving you the E of x, or I guess E of w and variance w. And then you find the probability of that thing occurring. I suppose greater than 0, if you think about 0 being like the midpoint, I'm assuming positive just means yes and negative just means no. So for instance, like positive just means that one has outweighed the other, negative means that the reverse has happened. I'm assuming that's what that means. I don't see why else you'd center it at 0 like that. This bit here is probably excessive. You have your mean, you have your standard deviation. They just, for some reason, love Z for, like they did it here as well. So I wouldn't worry too much about that bit. Nor would I worry too much about the entire question, but it's also just kind of interesting to see, like, why do we even do these transformations? And it has these sorts of applications here.
Probably something my school would put in the SAT.
Yeah, maybe. But, like, the thing that's weirdest about that is, I mean, maybe I didn't read it enough, but where is it? Where do they start doing this stuff? Sometimes I wish to find the expected value of a function of x. This is determined by... So it just tells you how to do it. Maybe there was an example here. But this kind of just looks like the regular old E of x, like you normally would. You don't have to do this stuff. Yeah, if you're interested in like following up on that in a bit more detail, this would be the chapter to have a look at it. But I feel like they didn't really explain too much about how to apply it.
I mean, I don't see why not. No, we'll see what we
Yeah.
can learn.
Anyway, that's there for you. It's all the way back in 13, the discrete.
Yeah.
I'm almost certain they don't touch on it anywhere else. But cool, I believe that took us to the end of chapter 16.
It's-
Do you want to move on to the next thing, or do you want to go back and do some of those things I said would be good for homework?
I think I'll leave this at home and then move on.
Sure. Okay, sampling and estimation stuff. So this is taking us back to pure discrete. The only thing that's really changing here is you're going to do one equation at the very beginning of your question. I'm just going to bring up the notes on that to demonstrate. Ability, sampling and estimation. And that's this idea of p hat, or even by extension p as well. This chapter differentiates between the population proportion and the sample proportion. Population you can think of as global, just all the possible elements that could exist with the attribute or in the set, and a sample just being a subset of all of that. The example I give here is just a math class. There's 3 boys, 5 girls in it, but, and that would give you the population proportion. But if I took a sample out of that, a group of 4 from that total, then the next thing you would calculate from that would be the sample proportion rather than the population proportion. So, as far as how it works when you're calculating these sorts of things, all you're ever doing is changing the p hat that's given to you and converting it to the x using the p hat equation. So just x, the number of things that have that desired attribute, over n, the total number of things in the sample. P hat meaning sample. If it was p, then this bottom bit would be the total population. That's all. So if we know p hat is a third, that means x over n is going to be a third. We also know that n is 3 since we're sampling 3 of them. So you have x over 3 is equal to 1 over 3. X is going to be 1. As soon as you get there, you can just ignore sampling and estimation for the rest of it, and you're now just solving like you would discrete. So you might do a counting methods thing, or you might just count it out. It's not too hard to do it when it's a low number of combinations. Fair enough?
Yeah.
Sweet. You'll also work with probability tables. The one that you're mostly used to is you'll have the outcomes on top and the probabilities of those outcomes on bottom. You can also slide in the p hat as well there. So you're essentially just converting your discrete number of x values into their relative proportion, which implies that pretty much every time you do this, you're going to have a range of 0 to 1 of your outcomes. 0 being it's not represented in the population at all, or sample at all, and 1 being just a full representation. So yeah, that's the main trick by far. Just convert your p hats to x's and then just move on with the stuff you're already used to. It's a pain in the ass to work with it in terms of p hat, like when you do your e of x's, for instance, going through and doing fractions rather than the numbers. You'd rather not do that. Yeah, so all the rules are basically the same, with the exception of just converting your p hat to x stuff. When it comes to the statistics, things are a little bit different, but the good news is these are on your formula sheet. So we have this weird thing of E of p hat being equal to p. It's more or less just because the terms are talking about the same thing. The expected, so we're normally thinking about expected value, which I guess I should change this wording, because in the context of sampling and estimation, this is now considered the expected proportion. Or in other words, what proportion do we expect across all populations? That is just p, the average outcome. And so it might seem weird that these are just the same thing. It's more so just to think of definitions. And the math actually supports it as well. Like, for instance, if you use your p hat table and you try to calculate the mean with your x times probability, or I guess in this case p hat times probabilities, you do end up getting the expected value you expect. Right? So for instance, a coin toss, you would expect the proportion to be 50-50 head-tail, which is why we get an expected proportion of a half. The math does support it, but obviously if you're a bit more sophisticated with your understanding of these things, you don't need to calculate any of this. You just know it's a coin flip, 50-50. Expected proportion, a half. Cool.
Yeah.
Variance, it does have a proof. Basically, the proof is rooted in the fact of p hat being a transformation on x. So if p hat is x on n, then simply means we should be able to replace both of those things. And then we use that formula we saw earlier, which is a way to rearrange things neatly. You basically treat the n as a coefficient on the x, and as such you can bring it out the front and square it, and well, when you then replace variance with what variance actually is in the binomial sense, one pair of the n's are going to cancel out, leaving you with a slightly different calculation for variance. You can also imagine that being a very similar reason why this is just p. E of x is usually np. When you replace x with x on n, the n's cancel out, leaving you with just p.
Yeah.
And yeah, standard deviation, just root variance, always. So there's nothing really different here. You're still just solving or finding n and p if you don't already have it, and then just chucking them in their relevant equations. These are always on your formula sheet. I think you only get variance though, so just be aware that you want a square root for standard deviation, literally always. But other than that, you're just plugging n and p in like you're already used to. Sample of 4 items, so n is going to be 4. A box of 10. There's 2 red, 8 blue. That's just telling you your p value. Just keep in mind what topic is actually being talked about. So in this case, it's the proportion of red pens. So you're going to use your p for red. 2 red out of a total of 10. Yeah, math. And then just because apparently I like typing, you could do this with a proportion table. I don't think you'd want to. Yeah. Those are the main things in sampling and estimation. Any questions so far?
No.
Cool. So the last thing we talk about is approximate confidence intervals. So it's a little bit different because...
I'm missing these things.
Hey?
But not understanding them. I remember seeing these things but never understanding them at all.
Yeah, okay. So understanding it, it does have a bit of a funky way to interpret what an approximate confidence interval is. I think first what we touch on is the equation for it. Kind of like how you do a confidence interval for x, where you're centered at the mean plus minus some number of standard deviations. This is more or less the same idea. P hat being the mean, p hat plus and minus some number of standard deviation terms, where z is going to be that number. So it's the same equation, basically. What changes is how we interpret what's actually going on. So because p hat is being used in this approximate confidence interval, it doesn't actually make sense to say something to the effect of p hat could be any value between some upper and some lower, because p hat is just some estimate you came up with when you did your sample. Let's say you sampled 100 people. In fact, I have an example somewhere. You surveyed 1,000 people and you got a p hat value of 0.55. All right, 55% were surveyed and they said they exercised on a regular basis. You plug in your p hat and your n, and you use your correct z value. So whether you use the z equals 1.96 or you go and use the in fact, yeah, let's have a look at that. The CAS way of doing it. Menu, statistics, confidence intervals, 1 prop z interval. You want to be here when you do it. You hop in there, just make sure you're splitting your p hat into an x and an n. So if 55% out of 1,000, so you're looking at 550 over 1,000. Well, of course you could just do, actually you probably should do the exact n that's used there. And then yeah, just hit enter on that. Control enter if it's an exact, and we'll see that it lines up quite nicely. You're looking for the C lower and C upper values for your upper and lower bound. It'll spit out the p hat value, and it'll spit out the n that was used to calculate that. I don't know what that is. I think it might be mean error. I just don't know what mean error means. So yeah, these are super simple to calculate on CAS. There's a function that's just inbuilt for it. So rather than have you go through and put in 1.96 and plus minus all those standard deviation terms, you just sort of got it in the CAS there. So the calculation's chill. The interpretation is the different thing. What you've done by calculating this is figure out the 95% of, yeah, we're 95% confident that anytime we do a sample of 1,000 people, the p hat value for that sample will be anywhere between this upper and lower bound. So I have a whole spiel on it here. So, you know, if you sample a group of 100, you might find the proportion of people of blue eyes to be 30 out of 100 there. So you would put a dot for your p hat value as 30. Then if you do it again, you might find that this time you get 27 out of 100. So you'll put your dot there. If you keep doing that over and over again, what you'll do is create a normal distribution of those p hat values. And the confidence interval you create from this distribution, that's what you're getting. It's an estimate of the range of p hat values given a single point estimate. I think this picture probably helps the most out of that. Is there any questions about that?
No.
No? Okay. That's what's going on there. You're using some initial sample as your point estimate for that particular confidence interval, and yeah, you're basically getting an estimate of this. That's why it's called the approximate confidence interval. A staple question that shows up basically all the time is to figure out your p hat and n from a given confidence interval. So a lot of the time they'll just give you the confidence interval and they'll say, hey, what was n? What was p hat? P hat is the easiest by far. It's always just the dead center of your interval. So just do the midpoint equation. Got it. From there, when it comes to solving the other variable, n, you're going to use one of the either upper or lower bound equations. Unfortunately, to my knowledge, there is no CAS thing you can do here for that, because it requires you to already have had a confidence interval. No, I guess that's just a bit of a cop-out. There could be a CAS function for this, but I imagine the inputting of it would be a bit annoying, because you'd have to put in what was lower, what was the upper, what was the C level. Yeah, should be doable, but I haven't seen it on the CAS yet. So we just sort of default to the actual equation. If you use the upper bound value, then use the plus version of the equation, and 1.96 is the standard use for 95% confidence interval. This will be in your formula. Sorry, not formula sheet. It'll be in your bound reference, because remember these are
Why
always
is
going to be.
it not 2?
Just because I want to be more accurate with it. It's if you do like the actual inverse normal, you do get 1.96 for a 95% confidence interval.
Okay.
Or for that Z value. It's basically number of standard deviations. It's close to 2. In Tech3, they do actually just tell you use Z equals 2 or use Z equals this as the equation. But
yeah, makes sense.
Yeah. So it'll be a good one to have in your bound reference, just making sure you're using that Z. Or worst case scenario, if you somehow forget that as well, you can just inverse normal it and get the Z from there. A lot of the time you're rounding anyway, so as long as you got the first 2 decimal places good, I'd be shocked if you couldn't round it properly to no decimal places, because you're trying to find n here. P hat's pretty much a guarantee. You can grab that, like just the midpoint, and that's it. If you forget that midpoint is the way to do that, then you just need both the upper and the lower, and you simultaneously solve, because now you've got 2 equations, 2 unknowns. So shortcut isn't required, but definitely nice to have. I think it's the last one. Yeah. The last kind of thing that they ask you is to figure out, hey, what happens if I increase n? Or what happens if I decrease n? What happens to the width of my confidence interval? We should know just intuitively that the bigger sample size we take, the more and more confident we can be, and therefore the width of the confidence interval should shrink, right? We can be more confident to say, yep, it's actually between 0.04 and whatever it is. It's currently 0.04 to 0.16. Maybe after we increase our n by 10 times, we can get it down to 0.01 to 0.9, 0.09, something like that.
Yeah.
The math for it, there's a bunch of ways you could probably do it. The way I would prefer to do it would be to look at the equations proportionally. So don't even bother putting in your p hat and n values. Like, don't even try to calculate them. Instead, say, okay, well, I know the width is just going to be 2 copies of my standard deviation term. All right, it's plus minus z times that standard deviation, so I'm going to do 2 copies of it. That gives me my width. Then, to see what happens to the new width, I'm just going to replace n with 4 times n, because we're 4 timesing n. The question has told us to do it. All I'm going to do there is do a bit of factorizing to make the 2 equations more comparable to each other. This one's 2z, this one's 1z of that thing. From there we can see this is 2 times bigger than that. And so just being cautious of the way you describe that, they ask to figure out by what factor will the width be decreased. If you just say the factor, you're at risk of a misinterpretation. So I would say, in my wording, it will decrease by a factor of this. Just making sure it's super blatantly obvious. Technically speaking, you should be able to just say 2 and get away with it. They ask for the factor of decrease, should be 2. You'd probably want to make sure you're bulletproof in it though.
Yeah, for sure.
Cool, that's those.
All right.
So yeah, you may or may not get to that. The main priority, I would say, would be the chapter sections that I mentioned before, because that seems like it's the only thing that it's holding you back a bit.
Yeah, would you mind messaging that to me?
Yeah, I'll do that now.
Cool. Thank you so much.
No worries. Take care.
Yeah, see you.